In today's talk, I'm going to be talking to you about the multiple reference frame, or the MRF approach that's commonly used in CFD to account for rotating components or turbomachinery. If you've ever wondered what the difference is between the MRF approach and the single reference frame approach, or the SRF approach, and the standard Navier-Stokes equations, then this is definitely the talk for you. I'm going to be looking at the various source terms, so the centrifugal force, the Coriolis force, and also the volume flux correction that's applied in the MRF approach. So if you've ever wondered what the difference is between these approaches and where the various terms come from, then this is definitely the talk for you. So get out a notepad, a pen and paper, be ready to take some notes, and I know you're going to find this talk extremely interesting. So to start off with the motivation for this talk, in the majority of CFD applications and simulations that we run, the meshes that we use are stationary. So if you consider the two examples I've got for you on the screen, I've got the example of a stationary aerofoil or a wing, and then some sort of piping or ventilation system. And for these common applications, what we do is we solve the incompressible steady Navier-Stokes equations. And that's all fine and straightforward because the meshes are stationary. But if we're looking at turbomachinery, so say a wind turbine, for example, or gas turbines, or an impeller, or some kind of mixing system, then we're interested in moving components. And the way we account for these in CFD applications is we create separate regions in the mesh, and then what we do when we solve the equations is we start by physically moving the section of the mesh at the start of each time step. So if you look at the image I've got for you there on the screen, we've got the majority of the mesh is stationary, and then there's a small coin-shaped region around the wind turbine, which you can see there in blue. And the way we account for this in the CFD code is we take that region, that coin that contains the wind turbine, and then physically rotate it by a small increment at the start of each time step. And of course, numerically, we solve the incompressible, unsteady Navier-Stokes equations, and that will allow us to get a solution. Now, this approach with mesh motion is fairly straightforward, it's well established, and it's easy to understand. However, there are a few problems with this sliding mesh approach, and that's really going to be the motivation for today's talk. Now, the problem with the sliding mesh approach is that we have to use very small time steps. So if we think we're physically rotating a wind turbine rotor, for example, or a gas turbine, then we're going to have to use a minimum of about 360 time steps per revolution. So you can see quite quickly, if you've got a wind turbine or a gas turbine and you want to calculate the response and the forces on those blades, then you're going to need a lot of time steps, particularly if you're doing 360 per revolution and you need to do 5 or 10 revolutions, say. So that's one problem with the sliding mesh approach. We need to use a lot of time steps, and that means our computation is very expensive and takes a long time. Now, the other problem with this approach is that we don't often have a good initial condition. So what do we use for an initial guess of the solution field? And what that means in practice is if we don't have a good initial guess, we have to use a lot more rotations of the rotor until we get a fully converged solution. And the other difficulty with the sliding mesh approach, you can see in the diagram which I've got for you there on the screen. And the issue is that the two meshes that separate the stationary region and the rotating region are not often conformal, particularly if one part is rotating relative to another. So you can see there in the diagram, I've got the non-conformal interface for you in red, and you can see that the mesh region on the right is going to be sliding or rotating relative to the region on the left. And that means at the end of each time step, those cells aren't necessarily going to line up. You can see there's an offset there. And CFD codes will have to do some type of clever interpolation algorithm in order to account for the non-conformal interface. And that can often make the computation more unstable and may diverge if the motion is too large. So what we're going to do in this talk is come up with a solution or a simple method that we can use so we don't have to physically slide or rotate a region of the mesh when we're solving for a bit of rotating turbomachinery. And the way we're going to do this is by thinking about the rotor that we're looking at, and imagine that rather than looking at the rotor from a distance, what we're going to do is we're going to solve the equations in a reference frame that rotates with the blade. So a way to think of this is if you were physically standing on the blade, what would the flow field look like from your position if you're rotating with the blade? And for the majority of applications, if we can manage to use this approach, then the solution and the flow field will be steady relative to the blade. And that means we don't have to run a lot of time steps, and we can get a very quick converged solution. And in most cases, you can actually use this converged solution for your results. And if not, the converged solution can always be used as an initial condition for a full sliding mesh approach. So that's the motivation for today's talk. Now, before I go into how exactly we're going to set up and solve the equations, what we're going to do is look first at a few definitions which you're going to need in order to understand the formulation that we're going to use. So the first thing we're going to look at is the axis of rotation and how we define an axis of rotation. Now, the example I've got for you on the screen is just a wind turbine, but you could use any bit of rotating turbomachinery you wanted instead. It doesn't have to necessarily be a wind turbine. And the axis of rotation, as you can see, all you need is to define 2 points that lie through the center of the rotor. So I've got x1 and x2 are 2 different points, and the vector connecting those 2 points I'm denoting as S, and we're going to use that for our axis of rotation. It doesn't matter which 2 points you use as long as they lie on the axis of rotation. And what we're going to do is the blades and all other components are going to be rotating around this axis. Now that we've got the axis of rotation, what we can do is define a rotation vector, which I'm going to use the symbol uppercase omega for. And the way we define a rotation vector is by multiplying the axis of rotation S by the rotational speed omega. So this is a very important point on notation, which you should think carefully about before diving into the derivations, where lowercase omega, that's the rotational speed, so how fast the rotor is rotating, but uppercase omega, that is the rotation vector. And we're going to need the vector in the derivations that follow. And to get one from the other, just a reminder, you multiply the rotational speed by the axis of rotation S. And the next thing to think about is the distance vector R, and the distance vector is going to be the distance between a cell in the CFD mesh and the origin of the axis of rotation. So this is very important to think about because we're going to be solving the CFD computations for, of course, every cell in the mesh, and every cell in the mesh is going to have a different distance from its cell centroid to the axis of rotation. So this distance vector R, which is the vector connecting the cell centroid and the axis of rotation, is going to be different for every single cell in the mesh. And that's very important to think about. And of course, what we're going to use this distance for is to work out the rotational component of the velocity relative to the rotating rotor. So just bear that in mind in the derivations that follow, that the rotation vector, omega, is going to be the same for every cell in the mesh. However, the distance vector r is going to be different for every cell in the mesh. And finally, before we look at the derivation, we're just going to talk a bit about relative velocity. So the notation I'm going to use in today's talk is to use bold symbol u for the global or the inertial velocity. And this is the velocity that you would normally be solving for in a CFD code. So if you're an observer standing far away from your wind turbine or gas turbine engine, for example, or your impeller, u is the velocity that you would see standing far away from the machinery. Now I'm going to use the subscript r to denote the relative velocity. So this is the velocity relative to the motion of the blade, or if you were standing on the blade, what you would see. And the way to think about these velocity components and how they're connected is with a velocity triangle. So the global or the inertial velocity given by the symbol u there is the large vector shown in green. And in the picture there, what I've got is I've got this section of the blade moving from right to left across the screen. So the blade is translating from right to left as we're looking at it. And of course, relative to the motion of this blade, there's a rotational velocity component, omega cross r, so the cross product there. And that's of course moving from left to right, the other way across the screen. And that's of course the rotational velocity component that the blade is going to see as it moves through the flow field. And then connecting up the velocity triangle, U with the subscript R is the velocity relative to the blade. So that's the velocity that the blade is going to see as it moves. And because these are connected by a velocity triangle, we can use that equation which you can see there in the image. U is equal to the relative velocity plus that rotational velocity component omega cross R. And that definition that I've got for you there is really key and is used in all of the derivations for multiple and single reference frame approaches. So now to move on to the derivation and to look at how we're going to assemble the equations for the multiple reference frame approach. Now what we're going to do is start with the steady incompressible Navier-Stokes equations that we saw in the first slide, and that's equation 4. You can see there we've got the convection term on the left hand side, and on the right hand side we've got the pressure gradient and the viscous diffusion term there on the right hand side. And what we're going to do at this point is we're going to substitute in that definition, equation 3, for the velocity in terms of the relative velocity into equation 4. So we're going to be substituting for u, which you can see there. And before we go into the derivation, just thinking about it for a little bit, what we're going to see is that u is going to be replaced by the relative velocity, and then we're going to generate some extra terms involving omega and r, and these are going to be extra source terms. So just thinking about how this approach is going to look, what we're going to do is we're going to be solving the equations in terms of the relative velocity. That's the velocity that the blade sees if we were standing on the blade. And we're going to have a few extra source terms there, omega and r. However, this will allow us to put the equations together in a steady formulation, which will save us a lot of compute time because we won't have to use the sliding mesh approach. Now, one thing to note in this talk is I'm not going to go through the full derivation with all the maths because there's quite a few pages of manipulation of terms. And what I've done is I've put a link for that derivation in the description to this video. So if you actually want to go through the maths yourself, you can do that. But what I'm going to do instead here is just present the solution, and then we're going to have a look at it and see what the terms actually mean and where they come from. And then if you want to go back to the derivation at any point, you can go ahead and do that. So the solution after the derivation is given for you there in equation 5. Now, notice in equation 5, the unknown in the Navier-Stokes equations is now the relative velocity. So that's u with a subscript r. We've replaced the global velocity with the relative velocity, and as a result, we've now got 2 extra source terms there, which you can see on the right-hand side. And it's common to refer to these source terms as the centrifugal and Coriolis forces. But for us, we don't really care about what they're called. All we need to know is that there are 2 additional source terms that we're going to have to apply at the centroid of every cell in the mesh. So at this point, all we've done is we've changed the solution variable that we're going to be solving for in the Navier-Stokes equations, and we've added 2 extra source terms at every cell in the mesh. And just having a look at those source terms, what you can see is because we've got the cross product with that distance vector r, we can see that cells which are further away from the axis of rotation are going to have a larger moment arm, and so going to experience a larger centrifugal force. And that's a way you can think about those 2 source terms if you're interested. And it's worth noting that with this approach, we solve for the unknown, which is the relative velocity. And once we have that, we can then use equation 6 as a post-processing operation to back calculate the global velocity u. And that allows us to get our complete solution that we're interested in. What I've got for you there on this slide is just a sketch of a typical setup that you might see for CFD calculations that use this approach. And what you'll see there in the diagram is that we've only got a single blade. And this is a very clever approach that many people use to further reduce the cost of the computations. If we use periodic boundaries on the sides of the domain, which you can see there, you only need to simulate a single blade. So you don't need to simulate the entire rotor. And this is going to cut down the cost of the computations. And with the formulation that we derived in the previous slide, what you can see there is we're now rotating with the blade. And an alternative way of thinking of this, and some people do use this, is to think that what you're doing is sitting on the rotor and spinning the domain around the rotor. So that's one way of thinking of it. Rather than sitting in a stationary domain and rotating the rotor, you're now on the rotor and you're spinning the domain around the blade instead. And this approach that we've gone through so far is often called the single reference frame, or the SRF approach. And the reason it's a single reference frame is the entire domain of the computation is effectively rotating with the blade. And we can't always use this approach, but this is one simple approach that we can set up in order to work out how to do a multiple reference frame approach, which I'm going to talk about next. So the motivation for the multiple reference frame approach is to think about, there are some scenarios where often we want to rotate the rotor, but we can't physically rotate the domain around it. And one example might be the mixing tank, which I've got for you there on the screen. And what you can see with this mixing tank is that, of course, we want to rotate the impeller at the middle of the domain, but we can't spin the domain around the impeller because we've got these fixed inlet and outlets, which we need to have in a fixed position. And likewise, we may have other equipment, we may have a tower or a connection for whatever our rotor is, or stator blades, for example, where we can't physically rotate the entire domain and we only want to rotate part of it. So the multiple reference frame approach is an extension of that single reference frame approach when we have stationary parts of the domain that we can't rotate. And how we would like to set this up is we now have stationary parts of the domain, and so in those parts of the domain we don't want to have any source terms because we aren't rotating anything in that part of the domain, and we'd like to have source terms in the region, only the region that's rotating. So a way to think of this for the mixing tank example, which you can see there on the slide, is that when we solve the Navier-Stokes equations, we'd like to not apply any source terms in that stationary region that contains the inlet and the outlet, and then apply selective source terms to the rotating region, which you can see there in blue. And in order to do this, what we're going to have to do is rearrange the Navier-Stokes equations again, but this time in terms of the global velocity. So that's u rather than u with the subscript r. And this requires a bit of careful rearranging and some maths. But as before, rather than go through all of the maths here in this talk, I provided a link to the derivation in the description, which you're free to go through if you want. But the result of rearranging these equations is the MRF equation, which you can see there in equation 7. And just taking a minute to examine the terms, what you can see there is the unknown in the equation is now the global velocity, so u without the subscript r. And we've now got a single source term on the right hand side, and we get this source term because of the rearrangement of the various terms in the equation. And what we've also got at this point is we've now got the equation in the form that we want it. We've written in terms of the global velocity, and we have a source term. And we're going to apply this source term in the regions that are rotating, but not in the stationary regions. That's why it's called a multiple reference frame approach. We're in a rotating reference frame in the bit with the impeller or the mixer, but we're in a stationary reference frame outside of that. Up until now, everything's been quite straightforward, of course, but there's one additional part that makes the multiple reference frame approach more tricky, and that is the modification of the convection term, which you can see there on the left-hand side. Now, if you look closely, you'll see that the convection term contains the relative velocity and the absolute velocity. And this is quite unusual in CFD, and you may not have come across this before, and we have to use some special treatment in order to account for the modification of this convection term. And what I'm going to do now is quickly go through that modification and how the CFD codes account for it at the end, and then wrap up the talk. So to understand how we account for the modification of the convection term, it's first worth having a quick recap of the finite volume discretization that's used in CFD codes, and that will help you understand how the convection term is modified. So just a reminder of how this works. What we do is integrate the entire Navier-Stokes equation over a cell in the mesh, and of course we can integrate each of the terms separately. We don't have to integrate the entire equation in one go. And what we're going to do is focus on the integration of that convection term, which is shown in red there in equation 9. And the way we simplify this term is by using Gauss's divergence theorem, of course, to turn the volume integral into an integral over the surface of the cell. And this doesn't matter about the shape of the cell at this point. Any cell will do, as long as it's a finite-sized region in space. And just a reminder for those of you who can't remember Gauss's divergence theorem, what it physically means is that the rate of accumulation of some quantity in the cell must equal the flux of that quantity over the surface of that cell. And I've got a small diagram for you there on the slide to help you understand that. If you think of the quantity as those blue spheres, which you can see, then if the spheres are accumulating in the box or in the volume, then there must be some flux of those spheres across the surface. And Gauss's divergence theorem basically says that those two balance. The rate that those spheres accumulate must equal to the flux over the surface. So once we've used Gauss's divergence theorem on the convection term, what we can then do is note that for CFD codes, we have cells that have a finite number of flat faces. And because they have a finite number of flat faces, what you can do is split up that continuous surface integral into the summation of the surface integral over each of the faces. And that's the simplification there in equation 11. And the next thing to note, and this is the trick in the finite volume method, is to note that because the quantities vary linearly across the face and across the cell, we can replace that integral with the value at the center of the cell. And in order to understand that, just have a quick look at the diagram on the slide. And what you'll see is that because the flow quantities vary linearly, you can just take the value at the center and then multiply by the area. And that will give you the same area in green under the curve. So the integral is the same as long as you take the value at the cell centroid, the face center. That's absolutely fine. So finishing off the simplification of the convection term, and we arrive at equation 12, which you can see there. We've got the finite volume integral of the convection term is equal to the flux across each of the faces of the cell of u, that's the velocity, multiplied by the volume flux across the face. And that can appear a bit confusing at first if you haven't seen this before, and so I've got a small diagram for you there on the slide to help explain. The way to think of this, of course, is that the velocity vector at the face center, uf, doesn't necessarily point out of the face, and this is the reason why we take the dot product of the two quantities. This gives us the component of the velocity normal to the face, or the component of velocity that's traveling across the face. And when we multiply that by the face area, that gives us the volume flux across the face. So this is the flux of momentum across all of the faces that make up the cell. And that's all that we've done with the simplification. For those of you who want further information, you can always look back at my talk on the finite volume method, and you'll see this in more detail if you're interested. But for now, all we're interested in is looking at how does the convection term change when we're using the MRF approach. And remember that in the MRF approach, we've now got the global velocity and the relative velocity in that convection term in equation 13 there. And if we go back to the finite volume derivation that we've just done, what we see is that the volume flux now contains the relative velocity in red rather than the global velocity. And the way that we account for that in the MRF approach is by making the same substitution that we did before. And that means substituting in for the relative velocity in equation 15 into equation 14. And that's a very simple substitution, and all we do then is from equation 16 split up that into two components, and what you see is that you've got the original convection term there, which is indicated by the underbrace, and then we've got this additional term which is often called the flux correction. So the first term in the convection term becomes exactly the same as you would have had in the Navier-Stokes equations, but we've now got this second summation, which is called the face flux correction. And that's a modification that we have to make when we have rotating zones in the MRF approach. So one way to help you think of this physically, because we've been through quite a lot of maths in those past few slides, is to think physically about what's going to happen in your simulation domain when you set up with the MRF approach. And what will physically happen is in the regions that are rotating, So the region around the impeller, which you can see there in blue, there are of course going to be extra source terms because that's rotating. But in addition to those source terms, we're also going to correct the volume flux on the faces of all the cells. And I've got that for you there in the image. So there's going to be a source term and we're going to correct the volume flux. And that's how the MRF approach works. So just to summarize this talk and what I've been through, the main points to note are that in the multiple reference frame approach, or the MRF approach, the Navier-Stokes equations are still solved in terms of the global or inertial velocity that you're used to using in CFD codes. However, we make two modifications to any regions in the domain that are rotating. So around a wind turbine rotor, a gas turbine rotor, or an impeller in a mixing tank, for example. And those two modifications are, we add an extra source term, which is given by omega cross product with R, and then we correct the volume flux on the faces of each of those cells. So there are only two modifications, and those modifications are relatively easy to implement in CFD codes. And if you go into the source code in OpenFOAM, for example, you can quickly find these two modifications when the MRF approach is used. And the final flag for this talk is if you want to have a look at the derivation, they're both in the description below the video if you want to actually see how the maths is done. So that brings me to the end of the talk. I'm really happy with how this talk went, actually, and I'm really glad that I could actually bring out the two key points of the MRF approach, which are the additional source term and also the volume flux correction on the faces of the cells. Because it's quite difficult to actually find information on how the MRF approach actually works if you look online at the various sources. So if you found this talk useful, let me know in the description or the comments. Tell me how you thought it went. Is there anything else you'd like to see on this topic? I'm thinking of doing another video on the mixing plane and frozen rotor approaches that are useful for gas turbine engines and for turbomachinery that has rotating and stationary components. So if you'd like to see that video, or perhaps you have any other ideas of videos you'd like to see, let me know in the comment section, and I look forward to hearing from you.